Hey guys, what is happening? Welcome back to another video. Today we're going to be talking about iron losses versus copper losses. We're going to dive into the details as to exactly what these terms represent, how it happens within our brushless motor. We're going to look at how manufacturers are able to actually reduce small parts of what we're seeing here. Then we're going to perform a very small calculation to get an idea as to the impact of both of these terms in terms of our efficiency of our brushless motor. We're going to start off by talking about copper losses within our brushless motor. Now, copper losses is a lot more easy to understand than iron losses. It's quite simple when you break it down. Essentially, copper losses are losses that occur within our windings of our brushless motor. The windings of our brushless motor are internal to the motor, and each one of those windings has a resistance to them. That resistance proves to us that wires are not 100% efficient. As with most stuff in life, we never see 100% efficiency. Wires is no exception to that rule. We always have a resistance. Now, motor manufacturers want to be able to reduce the amount of resistance that you have within a motor because that is going to improve the efficiency within that motor. We're able to do that using a couple different methods. The first method is the diameter of the motor winding itself. If we go ahead and look at a motor diameter winding here of a unit of 1 diameter, and we look at one versus this guy here at 1.5 diameters, we know that as long as this motor winding is made from the same material and it has the same length, that we would expect the winding with a bigger cross-sectional area or diameter to have a lower resistance. A way you can sort of equate this when using water, for example, water flowing through a river, you're able to flow more water through a river if that river is wider. If that river was more narrow, it's going to be more difficult to push the current of water through that river. Same idea happens within our wires. A lot more easy to pass current in a larger diameter wire. Motor manufacturers will use this to their advantage in order to reduce the RM value, which we'll get to very shortly, within the motor. That's essentially the resistance of the brushless motor winding. Now, another thing that is important for motor manufacturers is to make sure that they pack the motor with as much copper as possible. Why? Because if you are able to pack it with the most copper as possible, you can further reduce that RM value, the resistance of the motor. So let's see a calculation as to how we use these values. Now, we talked about RM. RM here in our example is going to be 0.023. We also have IO of 3 amps. The current that we're going to run this brushless motor at is 60 amps, and the voltage that we're running it at is 22 volts. Now, I'm sure you've probably seen both RM and IO values on a data sheet for a brushless motor. You would see this in the specification area where you'd see the kV of the value, the kV value of the brushless motor as well. So when we go ahead and use what we have here, we're going to use the RM value as well as the current that we're running the motor at to produce the power in terms of our copper losses. So this is direct power that goes into waste heat. None of this is good. Wire having a resistance wants to oppose the flow of current, which means you produce heat. So when we go ahead, plug the numbers in, 60 squared multiplied by the 0.023 gives us a total power loss of 82.8 watts. So now let's see what we get when we start talking about our iron losses. Well, what we do with iron losses is we break it down into 3 separate components. We start off with hysteresis. Hysteresis, in order to get a good understanding as to what this means, I've drawn up this very simple sort of image here. We have this known as our stator tooth. I've taken one tooth and I've put these electrical wires so that it looks like it's wrapping around. We have a cross-sectional area here that you're able to see. Now you can imagine if we were to have a magnet, it would be rotating on the outside like an outrunner in this direction. These stator teeth would then go, in all the circular pattern all the way around the motor. And what we're looking at is 2 different examples. In this case, we have a positive current flowing through our electrical windings here, the red circles. And in this case, we have a negative current flowing in this number 2 example. Now, the reason why this is important is because the current flowing through in a positive direction is going to give you, let's say, for example, a north pole in terms of your magnetic that you're forming, the magnet here. And if you reverse that, you're going to have the opposite magnetic pole produced. So let's imagine the positive is going to produce our north pole and the negative is going to produce our south pole. Now what's happening in the motor, specifically our iron core, is this hysteresis thing that we're talking about. When we go ahead and have our core magnetized so that it produces a north pole, internal to the structure of the core, everything's trying to align itself to produce that north pole. Then what you do is you flip the current and then you create a south pole. The material has to then realign itself so that it produces the south pole. Every time this happens, there's resistance to the core wanting to make that change. This produces what is known as part of our iron losses in the form of hysteresis. The second part that we have here is known as eddy currents. Now we break down eddy currents into a couple different forms that we do see in our brushless motor. The first form that we have here is eddy currents that are induced in the core when a magnet is moving. So if we go back here and look at an example, if we have a magnet and this is on our rotor, we go ahead and rotate that rotor. We're passing that magnet by a tooth on their iron core. We can represent this more simply by looking at a bar magnet and a metal sheet. So if we take a small metal sheet and then we take this bar magnet and we move it into the sheet, we are going to produce eddy currents in the form of circles. They're always in the form of circles. We're going to produce that in the metal material. Now that is current that is flowing in a circle in the material. It's going to go in a certain direction. If we go ahead and pull the magnetic bar out, you're actually going to change the direction of those eddy currents in the sheet of material. This is happening as a magnet passes by the stator tooth. You're going to have these eddy currents being produced or induced in that metal material. This is going to create, in the form of heat, wasted power for us. This is in no way good to us. It's complete waste of energy when we're talking about that sort of thing. Now, eddy currents can happen also in a second way here. We can also get eddy currents produced when a magnetic field is changing. Much like what we showed here, a positive current is going to, create the north pole for us, and then the negative current is going to produce the south pole to us. Every time this is happening, you're also getting eddy currents being induced in that iron core. You're going to have the circle of eddy currents being produced, and that again is going to create inefficiencies when we're talking about iron losses. That's the whole idea behind it. Now, all of these eddy currents is going to oppose our magnetic flux. You can imagine if you have a north pole produced here, that is giving off magnetic flux. It's a force, a magnetic force that you're actually able to measure. When we go ahead and have eddy currents in the material, or specifically our iron core, that is going to create the opposite magnetic flux. So let's say you're creating a north pole, the eddy current that is happening within that metal core is actually going to produce the south pole. And then what you get is a subtraction of the total amount of flux that you're trying to achieve. In other words, it's going to reduce the efficiency of the magnetic flux that you're trying to create, which then goes ahead and adds itself to iron losses. So we look at one way that manufacturers are able to reduce the amount of eddy currents within a brushless motor. They're able to do that, and I'm sure you've seen it if you've taken apart a brushless motor, that our iron core is produced by small, thin sheets of metal all sandwiched up against each other. Each one of those laminations has a small amount of insulation, and each one of them are very thin. In order to reduce the eddy currents, you make the laminations very thin, which restricts the amount or size of these eddy currents that you can produce. If you decrease the laminations even further, you can also reduce the eddy currents further, although you do get into other trouble when you go through that sort of idea. But this is definitely one way that motor manufacturers are producing laminations to reduce the amount of eddy currents that you see within a brushless motor. Now you understand why we use these laminations in our motors. Another area that we need to talk about is frictional losses that occur within our brushless motor. Now, frictional losses will occur primarily from the bearings. Again, just like we noticed here with their wires, they are not 100% efficient. Same with our bearings. We know that bearings are the most effective at doing what we're looking at them to do here in this case, but they do produce an amount of friction. When we go ahead and measure our iron losses, we're looking at the no load current, which is represented by IO. Our no load current is going to also consider the frictional losses when we spin that motor up at no load at a specific voltage. Now let's take what we've learned and apply it to our formula and calculate the amount of iron losses that we'd expect from this example that we've already covered. We go ahead and look at our system here, and we notice that we have to plug in the IO value of this motor at 3 amps. We take 3 amps and we multiply it by the voltage of 22, and that gives us a total power loss in the form of iron losses as 66 watts. That would be the iron losses, and then we can go ahead actually add the iron losses to our copper losses, and we get a total amount of losses of 150 watts. When you consider 150 watts of lost power, that's quite a bit. You can probably get a small 40-inch wingspan airplane easily above 100 kilometers an hour with that amount of power. It's quite a bit of power, but then when you look at the amount of power that you're actually getting out of the system, if you take the 150 and it's a 1300 watts you're getting out of that system, that's going to make a brushless motor about 88% efficient. That is very good when you're talking about brushless motors, or if you're even talking about anything. If I were to be able to record this video in only 88% of the time that button or red light has been flashing, that would be pretty awesome. In fact, it's much lower than that. And even 88% for a lot of different industry level things is quite good. So there you have it. We've gone through this topic of iron losses and copper losses. We looked at all the different parameters there and reasons why we get these sort of losses. I hope this video was helpful and you have a good understanding as to why you see the IO value and RM values on spec sheets. Please hit that subscribe button to help support the channel, and I hope to see you in that next video. Thank you for watching.